So now we want to find the critical points for this thing, and that means those values of x, so want critical points. So we want to know which values of x have f of x being 0. So what we want to do is solve, this is f of x, right? X just means theta omega, the pair theta omega is x. We want to solve this, f of x equals 0, 0, the 0 vector. And whatever values of theta and omega make this true are going to be critical points. They will be equilibrium solutions. So there will be solutions where there will be values of theta and omega where if your pendulum has those theta omega values at any given time, then it will just keep those theta omega values forevermore from that point. So we are finding the equilibrium solutions. So which values of theta and omega solve this? Well, we can see which values of omega. That part's easy. Omega equals 0. But what about theta? The second equation here is get rid of this non-zero constant. It's just sine theta equals 0, right? So there are a bunch of solutions to that. Basically, theta equals n pi for any integer n, right? So sine theta will vanish for when theta is 0, pi, 2 pi, 3 pi, negative 2 pi, etc. So let's start making our picture and draw the critical points. We've got this infinite family of critical points in the phase plane. So the phase plane shows, each axis is for one of my dynamical variables. So one of them is for theta, the other one is for omega. And I have found an infinite family of critical points. There's a critical point, so they all have their omega coordinate being 0, so they all live on this axis, the theta axis, where omega equals 0, but they all have different theta coordinates. There's one for each integer multiple of pi here. So there's a critical point, let's make them yellow, there's a critical point at 0, 0, but then there's also one at pi 0, theta equals pi, omega equals 0. And then there's, let me space these out more, and then there's one at 2 pi 0, 3 pi 0, and so on. Negative pi 0, negative 2 pi 0, negative 3 pi 0. So I might label them like this, or now that I've done it, I actually think it'll make everything too cluttered, so let me not do that. Okay, so each of these points, if the system's state is ever any one of these yellow points here, then it will remain there forever. So let's think about what these points stand for. What's 0, 0? That's theta equals 0 and omega equals 0. So the angle, remember theta stands for this angle of displacement from the vertical, and omega is the angular velocity. So if both are 0, this situation, that stands for the pendulum just being hanging down like that and not moving, being at rest. Then it'll just stay there forever like that, doing nothing, right? And actually, so is this one. Remember this one was 0, or 2 pi 0? Theta equals 2 pi and omega equals 0. If theta is 2 pi, that means your angle of displacement from the vertical is 2 pi. That's just another way of saying it's 0, right? An angle of 2 pi is the same as an angle of 0. So it also corresponds to the situation where the pendulum is just dangling down at rest, doing nothing, will do nothing forever. So these are equilibria, and they correspond actually to the same physical situation. So this is an interesting phase space where there are many points that really correspond to the same state, and the same state just has multiple names. Now what about this one? And this one will also be the same since it differs by theta. It has a theta difference of 2 pi. So what about these? What state do these correspond to? Or this one? Or this one? What do these correspond to? So let's say this is our center point. Pendulum rotates about that. These correspond to theta equals pi. So the stick is standing straight up. and the pendulum is just balanced, standing up like that. This is why it matters that it be a stick and not a string. If it were a string, it would just fall, right? But the stick can fight against the gravity and provide force, holding the pendulum up. It's a very unstable situation, right? If you just touch it a little bit, it'll fall. So probably these will be unstable critical points. So I don't know if this picture is making sense. The idea here is that this is the fixed point that it rotates about. This is the path that the pendulum is constrained to, and this is a situation where it's just standing straight up, balanced, and it's at rest. Omega equals 0. It's at rest. So this phase space is not physical space, right? If you move up and down in the phase space, that's corresponding to your system changing its omega, its angular velocity. So being here means it's at rest. Okay, so we just have these sort of alternating. We have two types of critical points. Some that correspond to the being at rest and pointing down, and some that correspond to being at rest and balanced up top. So far we've got the constant solutions, right? These are all constant solutions to the differential equation. The interesting ones are the non-constant ones. So if I start my pendulum, displaced a little bit, like here, then what's going to happen to it? It's going to move in the phase space, right? But which way and how? How does it move? What if I start it here or here? How will it move? Well, the differential equation prescribes how the motion must be. X prime, the velocity vector that tells you how it's going to move in the phase space, so it's going to move with velocity f of x, f of wherever it is. So this vector. So wherever you look in the phase space, some place with certain theta and omega coordinates, you'll have to evaluate this right-hand side here at that location, and that will give you a velocity vector that tells you how you're going to proceed from there. What should be your instantaneous velocity from there if you want to be a solution trajectory. So this, let me rewrite the differential equation down here. So this right-hand side of the differential equation represents a vector field. It gives you at each point some vector that points in some direction and says which way you're going to go from there and how fast. So what we're going to do, since this is actually kind of complicated looking, what we're going to do is basically zoom in very close to different ones of these and figure out what's the closest linear version of this function that we can come up with, and then whatever we come up with will be more and more accurate the more closely we zoom in to each of these locations. So we're going to have to do this at each location. So you will see what I mean. So let me start by zooming in here and blow this up. Then I've got this critical point at the origin, and I've got increasing theta that way and increasing omega that way. So I sort of remember that my theta and omega axes point that way and that way. And that location is theta equals 0, omega equals 0. So the way to do this is to find what's called the Jacobian derivative of this vector-valued function of two variables at this location, theta equals 0, omega equals 0. So this is an unfamiliar concept. I never introduced it in this course, and it's actually something you learn about in Math 6a. So this is one reason I'm putting it in the very last lecture and making it something optional to look at. My hope is that it makes sense that we might want to find the closest linear function to this one, and then maybe you can take it on faith for now that the Jacobian derivative is some kind of construction that gives you that gives you the closest linear function to this one near a particular point. So here's mechanically the way it works. First, create a 2 by 2 matrix, which is made out of the different partial derivatives of this. That's another thing you learn in 6a, partial derivatives. So my first row will be the derivative of this with respect to theta, that's 0, and then the derivative of this with respect to omega, that's 1. My second row will be the derivative of this with respect to theta, that's negative g over L cosine theta. And then my second component will be the derivative of this with respect to omega, that's 0. Then, the way this works, just mechanically, let's just accept that this is how it works. If you want the closest linear approximation to this function, the closest linear function to this function, the matrix that most closely represents this function, near the point 0, 0, theta equals 0, omega equals 0, what you do is take this thing that you built and you plug in theta equals 0, omega equals 0. So when you do that, you get, well, there's no omegas to substitute anything, but there's theta. If I plug in theta equals 0 here, I get cosine of 0 is 1. So this is what I end up getting. So if you zoom in close enough here, what I'm claiming is that when you blow this up, you zoom in very close there, what you see is very, very close to this differential equation system. Theta prime, omega prime equals that matrix applied to theta omega. Which matrix? This one that I got by plugging in theta equals 0, omega equals 0. So 0, 1, negative g over L 0. And we know that just from this coefficient matrix, we can learn a lot about what the phase portrait looks like here, right? So let's do that. So if I have this, how about I zoom in and actually just write things down very close to this. So if I have this system of differential equations, maybe the first thing I can do is check the determinant of the coefficient matrix. The determinant is g over L, right? Which is positive. Okay, so it's not a saddle point. Great. What else can I figure out? The trace is 0. So if the eigenvalues were non-real, then they would be purely imaginary, because the trace tells you 2 times the real part, so the real part would be 0. So this is either purely imaginary eigenvalues, or it could be that the eigenvalues are real, in which case, let's see, if the eigenvalues were real, could you have the sum of the eigenvalues be 0? I don't think you can have the sum of the eigenvalues be 0 if they're the same sign, right? So we're in a situation where the determinant was g over L, and that's greater than 0. So the eigenvalues, if they're real, definitely have either they're both positive or they're both negative, because their product is positive. The determinant is their product. Okay, sorry, I think I'm making this confusing because I'm trying to figure it out kind of live. So how about I write it down as kind of a tree like this. So either the eigenvalues are real, or the eigenvalues are complex, meaning non-real here. So real or complex. And then I know the determinant is greater than 0, right? It's g over L. So if the eigenvalues are real, then they can be both positive or they can be both negative. That's the only way that their product can be positive. The determinant is their product. In the both positive case, but I can see from the trace that the sum of the eigenvalues is 0, right? The trace is 0, that's the sum of the eigenvalues. So the eigenvalues add to 0. If they're both positive and they add to 0, they must both be 0. If they're both negative and they add to 0, they must both be 0. So because the trace is 0, these both lead me to the conclusion that the eigenvalues are both 0. But if the eigenvalues are both 0, then this is just the 0 matrix that I'm looking at, right? This would just be the 0 matrix. So, and it's not. Clearly it's not the 0 matrix. So it must be that the eigenvalues are non-real. But now since the trace is 0, I can see that they're purely imaginary, right? So purely imaginary eigenvalues, that's a stable center. That's the kind of phase diagram that I would expect from that. Okay, so by analyzing this, I reach the conclusion that I'm looking at a stable center. So let me show kind of the picture that you would expect, maybe some circles or ellipses or whatever, depending on the units you set up. And I guess they go in a certain direction. Let me figure out what direction they go in. If I plug in a point here, so theta being 1 and omega being 0, then what comes out is 0 and then something negative, so 0 horizontal component, and then it points down, negative vertical component, so like that. So it must be going that way. Yeah, so that's the picture that you expect to get when you zoom in. That's if you zoom in pretty close. So here I expect to see kind of this picture, at least nearby. And then maybe elsewhere there's some weird crazy stuff going on, right? But at least nearby I expect to see this. Now I actually get the same. So how did I get this matrix, 0, 1, negative g over L, 0? I got that by evaluating this, the so-called Jacobian matrix at theta equals 0, omega equals 0, right? So for the other points, I would do the same thing, but I would evaluate at those other points. If you focus on this point, theta is 2 pi, and omega is 0, right? 2 pi, 0. So then I would go plug in 2 pi for theta, and I would get the same result here. And so I would get the same picture at this point. It would also look, near to this point, it would also look like a stable center. And similarly for this point. If I put in negative 2 pi for theta, I get the same picture. Let me keep it small. The picture holds, the extent to which the picture holds is the extent to which you have zoomed in, basically. That's when it's guaranteed to hold. So what about these other ones? Well, for these other ones, you plug in, so let's try this one. Pi, 0. So let's zoom in on that and see what picture we should get. So if I zoom in here, let me put that down there. So now it's going to look like this Jacobian matrix, but evaluated at theta equals pi. So it looks like theta prime, omega prime equals 0, 1. No, there's a 0 there. And then this was negative g over L cosine theta. But I'm putting in pi for theta. So I just get g over L, positive g over L. Because cosine of pi is negative 1. And then here, theta omega. And this is not strictly true, actually, what I'm writing. It's not exactly like this. It's like this if this were treated as your new origin. So you sort of have to pretend that we're shifting the not pretend, you actually have to shift the theta omega axes to here so that the new 0, 0 becomes here. Then it's as though you're looking at this differential equation. So do a shift, and then it's as though you're looking at this zoomed in very close here. Then what would you see? So focus on this matrix. What's the determinant of this matrix? It's negative g over L. That's negative. That's easy. It's a saddle point. So we have a saddle point here. Those are always unstable. Okay, well that's what we thought, right? These situations here, 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 where the pendulum is just standing up balanced, that should be unstable, right? Turns out we get a saddle point in the phase plane. So it ends up, so for saddle point you need to figure out what are the two eigendirections. It ends up looking like this. You can figure out the two eigendirections by actually going and solving the eigenvalue problem for this matrix. But it ends up looking something like this. Okay, so I just went and did it here in Mathematica, solved the eigenvalue problem for that matrix. And here are my two eigenvectors, this one and this one. And this one has positive, positive components, so that corresponds to this direction. And what's the eigenvalue associated to that seems to be this one, which is a positive eigenvalue. And then this eigenvector is this one, and that has the negative eigenvalue. So that tells me that solutions along this line, the straight line solutions, go out here, and they come in here, like that. And then everything else looks all saddle pointy, like that. So that's the picture near those points. So let's go and try to build a global picture. This is getting kind of cluttered, but let me just fill in just those points. So we have, I already forgot what it looks like. Okay, this way it goes out, this way it's coming in. So out, in, and then it's going to repeat for the same reason that it repeated before. Is you're changing by 2 pi, you're changing theta by 2 pi, right? So you're just plugging in into here, you're plugging in, rather than pi, maybe minus pi, or 3 pi, minus 3 pi. You get the same results. So like this, here also, here. We can fill in the in-betweens. Okay, let's try to make a cleaner version of this. Okay, here's my cleaned up phase plane with all the equilibria. So all omega equals 0, theta equals 0, theta equals pi, theta equals 2 pi. And here are the local pictures that we figured out that work when you zoom in on these equilibria that correspond to the pendulum hanging down. So this is saying if you're near to the pendulum just hanging down situation, so you differ from it by just a little bit, either theta differs from it by a little bit because it's displaced by a little bit from the hanging down situation from theta equals 0, or omega differs by a little bit, so it's not at rest, but it has a little bit of angular velocity. Then in all of these situations, you get oscillation, right? This is the pendulum swinging back and forth. That's what all of these represent. Okay, and here's one eigenvector filled in for the local pictures at the saddle points. And there's the other eigenvector. And there's more stuff filled in. So let's think about just one of these example situations. So let's start with this one. So let me sort of zoom in on this one. Looks like I didn't draw enough of it. There's also this part. And this is there's a whole family of these, right? I'm just only drawing some of them. Okay, so I just want to zoom in on this and think about what this physically represents. So if you are exactly at this yellow dot, that we decided that represents theta equals pi, so that represents, and omega equals 0, so that represents just being balanced, standing like this. And you can imagine that if you tip it one way or the other, it will fall that way and start swinging around, right? So this is balance. If this is the fixed pivot, then it's just balance standing up. Okay, so now there are two ways we can imagine perturbing from that situation. We can either change theta by sending it either this way or this way, without changing omega very much, right? So moving a little bit this way or moving a little bit this way from that situation corresponds to moving its position, but still releasing it from rest. So omega still equals 0 from the beginning. So if I move it here, for example, then I'm like taking it and then I'm changing the angle a little bit, and then I'm letting it go from rest. Then what's going to happen is it's going to fall, swing up, approach that point, and then fall back again. Swing up, approach that, fall. Okay, so you see what's being suggested here is that we follow this kind of weird shaped, almost ellipse thing, but not quite. So we end up in an orbit. We end up looking like one of these. What about when you're here? What happens there? What does that represent? You're still starting from theta corresponding to pointing straight up, but then you're giving it a flick, right? You're kind of giving it some angular velocity. Then what happens? It goes around and around. Now it has enough energy to go over the top each time. So what you will end up seeing actually is something like, you will end up going down, down, down. So this corresponds to the angle coming back down, and then coming up, and then going over again, and over again, and over again. Okay, so all of that is a little bit difficult to deduce from just the critical point analysis. So I think the critical point analysis gets us this far, but if you can try to build a global picture, and it's harder. I think it requires more of a more work explicitly solving the actual problem. But what you end up with, and you could imagine that this is the way it works if you just try to glue these pictures together in any way that makes sense. You end up with this, which I'm not drawing very nicely. And these actually end up connecting up. So they're not so straight, really, right? They're only straight when you zoom in. That's where the approximation part comes in. And these kind of blue eyeballs separate different kinds of behaviors. So here you've got, within any one of these eyeballs, you've got swinging back and forth. And above the eyeballs, or below, you've got, above you've got rotating about the pivot in one direction, and below you've got rotating in the other direction. So here you've got a flow to the right, and here you've got a flow to the left. Okay, so what I hope you're getting out of this is not necessarily any particular computational technique, but what I hope you're getting out of this is that nonlinear systems of equations can look very interesting. The possibilities, there's a much richer world of possibilities than just looking at linear systems. But if you zoom in on any of the critical points, then you see your familiar pictures of stable center or saddle, or you can have stable nodes, unstable node spirals, and all that stuff.